Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be looking at trends that exist in ionization energy. Let's get started. Ionization energy is defined as the minimum amount of energy that's needed to remove an electron. And so with each iteration of removing electrons, it's going to become harder and harder to remove another electron because now those are being pulled in tighter towards the nucleus. And so as we do our first ionization or our second or third, we would expect that the overall energy needed to remove each electron is going to get higher and higher. Now, in regards to the trends that we're going to be looking at, we have to think about, well, which elements tend to like to lose electrons? And so the general trend that we see that it happens with the first ionization energy is that the larger the effective nuclear charge on the electron, the more energy it's going to take to remove it. And so think about it, those are the nonmetals, things that don't want to lose electrons. And so our trend for our ionization energy is going to increase towards are nonmetals because they need more energy to kick out an electron. They don't want to lose electrons. Our metals like to lose electrons, so it doesn't take that much energy. So that's why you have that smaller value. Now, in regards to what's going to happen as we look at up and down the periodic table, well, the further away an electron is from the nucleus, the easier it'll be to remove it. And so the further away things will be those found at the bottom of the periodic table. So the amount of energy that's needed is going to increase up the periodic table, okay? And so that's going to be the general trend for our first ionization energy. When we say first ionization, that's just referring to removing the first electron. Second ionization will be second electron, third ionization, fourth, so forth, okay? And so you can see the elements as what you would expect that require the highest ionization energies within their rows, within their periods, are your noble gases. They don't want to lose electrons. So if you want to come in there and kick out an electron, you need a whole lot of energy to get it out of there. Whereas your alkali metals, your group 1 metals, require low amounts of energy to remove that electron. Okay. And again, there are specific values associated with each. You're not so much responsible for knowing the exact values, but how the trends exactly apply. All right. And so if we looked here, if we wanted to do some comparison and wanted to make this prediction for aluminum versus sulfur, well, aluminum is found to the left, sulfur is to the right. So we would expect sulfur would require more energy to remove an electron. Between arsenic and antimony, Sb, you would expect that As would require more energy. It's further up. Its valence shell is closer to the nucleus, so more energy is required. And between nitrogen and silicon, again, nitrogen is further up and to the right, and so we would expect it to have a higher ionization energy. And then between oxygen and chlorine, we can't really tell because they have opposing trends. All right, so here we want to choose the pair between these two that would have the highest ionization energy. So between magnesium and phosphorus, if we find those, you would say that phosphorus should have the highest ionization energy because it's found further to the right. Between silver and copper, well, we would think copper would have the highest ionization energy because its valence electrons are closer to the nucleus. Between calcium and rubidium, well, calcium is further up and further to the right compared to rubidium, so we would select calcium. And for phosphorus and selenium, you notice where they're located, they're both have opposing trends, so we wouldn't be able to declare this, okay? Now, there are some irregularities that exist in these trends that we're seeing, and this is specific with group 2A and 3A and group 5A and 6A. And so this is more FYI knowledge, just so you can see what's going on here. And so if we look at the orbital diagrams for something that's found in 2A versus 3A, the groups, if you look at beryllium versus boron here and ask yourself, well, which one would it be easier to remove an electron? And you would think that if we looked at the trend is telling us that boron should require more energy. However, what we see is the fact that if we wanted to come in and remove an electron here, we have to actually break up a full shell. And so breaking up a full shell actually requires more energy than just trying to kick out this one. And so in this case, your 3A is going to actually be less energy than your 2A. All right. Or similarly, if we look at something that's found in group 5 and 6, same thing applies where by just the trend itself, we would say oxygen should require more energy. However, when we're looking at this versus this, we're trying to come in and break up a half-filled subshell, which would make it more unstable. It's a lot easier to kick this electron out than break up that half shell. And so in both the cases of 2A compared to 3A or 5A compared to 6A, the 2 and 5 respectively require more energy than 3 and 6, okay? Because you're not breaking up that full sublevel or that half sublevel. Okay, so again, to ionize with beryllium, you have to break up that full sublevel, and that's going to cost that energy, okay? Same thing with nitrogen and oxygen. Breaking up that half sublevel will require more energy than the oxygen. All right. So we've talked about what happens when we're removing one electron, but what happens as we're removing subsequent electrons? Okay. Well, what happens is with each iteration of removing another electron, the amount of energy that's needed is going to go up. All right. And it's going to be a substantial increase. All right. Now, where you'll really see a big increase is that when you're going from a valence electron to now going into a core electrons, removing core electrons, that's where you have this huge increase occur. And if we're looking at a set of data, we can predict how many valence electrons something has based on where we see that large number jump occur. So like look at, for instance, here, something like sodium. Sodium is a group 1, so we know it has 1 valence electron. So the first energy, ionization energy, is shown for you. Now, if we wanted to remove a second electron, well, now we're dipping into the core. And so notice how there's this huge increase in the amount of energy that's needed for that second ionization energy. The fact that that huge jump occurred after the first ionization tells us that now we're dipping into our core electrons. Compared to if we looked at something like magnesium, which for the first ionization energy, remember magnesium is group 2, so it has 2 valence electrons. First ionization energy takes some energy. The second one takes more, but not like a substantial amount. But then that third ionization energy, well, now look at that huge jump. That fact that we have that huge jump is telling us we're now jumping into our core electrons. And so we can look at data to help us to figure out how many valence electrons something may have just by looking at the ionization trends. All right, so you can see here, if you look at this table here, something like aluminum. Well, aluminum, we have, 3 ionization energy shown. And then it's after that third one, we have that huge jump. So that tells us that there are 3 valence electrons, and then that fourth one is now dipping into the core electrons. Same thing with silicon. Silicon has 4 valence electrons. After that fourth ionization, that's where we see the huge jump. That's what we now know is we're dipping into those cores. Or phosphorus after the 5th one, sulfur after the 6th. So if you're given a set of data and you don't know what element you're dealing with and asked to figure out how many valence electrons that element would have, you look for how many iterations did it take before you see that huge jump. Where you see that huge jump, that is telling you where you're now dipping into the core electrons, and everything before that would represent your valence electrons. I hope this video helped you guys understand ionization energies and trends associated with them. Make sure you guys like, comment, and subscribe, and come back for more videos. See you guys later. Have a great day. Bye-bye.